Okay, the recording has started. Okay, good evening, everyone. The agenda for tonight is to go through tutorial 11. And okay, so let's get started. Okay, so what you see here is not just one op-amp, right? So far, the question that we have done up to this point is single op-amp systems. Okay, you just see one triangle, one triangle, one triangle individually. Now, what about this kind of question? This kind of question is a composite system. So what that means is many op-amps lined up together. Okay, they will produce an effect. So here you have your input. So whatever voltage source you hook it up, these three op-amps, each of them will do something individually and then have a combined effect in the output. Okay, so we can achieve a combined effect by placing multiple op-amps, each with different purposes. Okay, so you'll see as we analyze this question. So let us begin. So find the frequency response of the first stage for all frequencies. So the first stage is this one, to the leftmost. All right. Now, let's not even begin on part one of this question. Let us just simply take a look and see if we can simplify the question right off the bat. So remember, when we look at op-amps, the three rules that you need to think of: V plus equal to V minus, I plus equals to I minus equals to 0, and then just do KCL wherever possible. Okay, so not different from the last 2 weeks of our training. So looking at the op-amp system, there is something we can easily identify. Take a look at all the plus terminals of the op-amps. This one, and this one. All of them are connected to ground, correct? So their voltage value is 0. Okay, so immediately you can just label each of the positive terminals with 0, 0, 0. Yes, V plus is equal to 0 because all of them are connected to ground. And remember, the fact is V plus is equals to V minus. Okay, this is always the case for an ideal op-amp. So immediately, if the plus terminal is 0, I can immediately say that the minus terminal is also 0. So 0, 0, 0, right? All the plus terminals are connected to ground, so they're 0. Then all the minus terminals must be 0 also, because the fact is V plus is equal to V minus. And we have simplified our equation, simplified the op-amp system analysis quite rigorously already, just by directly observing this simplification. So now we can begin. So I just cropped out this image of the stage 1 down here so I can draw it more easily. And in fact, we should focus on stage 1 and ignore the other stages first. So again, I'm going to label here. Okay, so here's 0. Here must be also 0, right? Now KCL wherever possible, makes no sense to do KCL here, right? Because we say that I plus is equal to 0. I minus is 0, so there's no current directly flowing in here. So let us just do KCL on this node. Okay. So let us assume a direction. In my solution, I've assumed this way. So like this, current going in, current going out. So the current going out flows through, it will split at this node, it'll split here, and recombine here, and then come out through here. Correct? Okay. So that means we need to combine the capacitor, the impedance of the capacitor and the resistor together. Okay, let us just call this Z1. We just take down my solution here. Okay. So now we can do our KCL. So KCL at the negative terminal. We do, okay, so KCL means current going in is equal to current going out. So the current going in, this one, we have to express it as delta V over R. Delta V is V start minus V end. So it starts at here, it ends at the negative terminal, right? So V start minus V end is V1 minus V minus. But we know we already labeled V minus as 0. So just automatically put in 0. Divided by the resistance, which is R, equals to the current going out. So the current going out is this one up here, right? It goes through the capacitor and the resistor, this one and this one. And it flows back out here. So you see, it starts at here and ends at here, right? So the ending is V what? VI. Oh, sorry, V1. Oops. This one is VI. Sorry. Okay, this one is VI. Okay, I made a mistake because it was too small. I couldn't see the dot. Okay. So starts at V minus, which is 0, ends at V1 divided by the Z1. Okay, so let us just make V1 over VI the subject first. So if we get V1 over VI, we should get negative Z1 over R, correct? Now we have to find Z1. So we look at the arrangement in the box here, right? The arrangement is parallel. So we have to find the total impedance in a parallel arrangement. Okay, so we just use this formula. So 1 over Z1 is equals to 1 over impedance of the resistor, which is R, plus impedance of the capacitor, which is 1 over J omega C. Okay, omega C1, sorry. This is omega C1. Then if you make Z1 the subject, in the end, you should get 1 over R plus J omega C1. Okay, now we can sort this into here. Right, so V1 over VI will be equal to, okay, let me just solve it in slowly. So this, I put it into here, 1 over R plus J omega C1 divided by R. Okay, so this is a fraction inside a bigger fraction, right? So if I have a fraction A over B divided by C, this will become A over BC, right? So that means I take this denominator, multiply by this denominator. Okay, so simplify this, you will get 1 over the negative, this negative, I'll just put it to the top, okay? And then, oh, sorry, you get R, 1 over R plus J omega C1. That means here's our resulting solution, which is, I just expand this, so R times this and R times this, you get negative 1 over 1 plus J omega C1 R. Okay, so this is V1 over Vn. Let me check if I'm right. Yes, okay, I'm correct. So now we move on to question 2. Let me just move this down a bit. So question 2 asks you for the same thing, the frequency response, but now for the second part, right? So this is the input for the second stage. This is the output for the second stage. So it's just V out over V in, but they label it as V2 over V1. Okay, so again, we can see V plus is 0. That means V minus is 0. And then I will assume a direction. So let us assume like this: going in, going out. Okay, so KCL at the negative terminal, current going in, which is this one. So it starts at V1, it ends at V minus, and V minus, we already labeled it as 0. Okay, so V start minus Vn is V1 minus 0. So V1 minus 0 divided by, it went through these two things. So there's a capacitor there. We need to find the total impedance in a series arrangement, right? These are connected in one straight line, so it's a series arrangement. So let us do that. We have R plus 1 over J omega C2. Okay, equals to the current going out. So the current going out is like this. It goes out like this. It starts at the V minus, which is 0. It ends at V2. So V start minus Vn is 0 minus V2 divided by R. Okay, our objective is to make V2 over V1 the subject. So let us do that. So this can go away. This can go away. And then I will move R to here, move 1 over down here, and then move this negative sign to the left-hand side. Okay, so I will get R, negative R plus 1 over J omega C2, V2 over V1, right? And actually, this is the solution, right? This is the answer already. Let me check. Yes, this is the solution. Then here, the third stage, okay? Now they want V out over V in of the whole circuit for all frequencies. Now, you see, take note that this is asking for V out over V in. This is not V in, right? This is V2. Where is V in? V in is all the way at the start, at stage 1. So what they're saying is they don't want just the V out over V in of stage 3. They want the V out over V in of they want V out over V in of the entire assembly, okay? But nonetheless, we still need to do the V out over V in for stage 3 alone, okay? Just focus on stage 3 first. Before we can consider the whole system, we need to still consider only stage 3, okay? So let us focus on that. I'll explain why we need to focus on stage 3 first. Let us just do it alone. So, again, this is ground, so V plus is 0. Then V minus is 0. Then assume the direction, going in like this, going out like this. Then KCL at we can do KCL at the negative terminal. So current going in is, this one's current going in. It starts at V2, it ends at V minus, which is 0. And then the current going out is, it starts at 0, it ends at V out, right? So current going in is V2 minus 0 divided by R. Is that R or R1? Let me see. I cannot see. Okay, it's R1, sorry. Okay, let me check if okay, nothing's wrong. Okay. So divided by R1 equals to 0 minus V out divided by RF. Okay. We still want to make V out over V2 the subject, which is the frequency response of stage 3 alone. So this one is gone. This one is gone. I'll move this down here. Then RF can come up to the numerator up here. So V out over V in is equals to negative RF over R1. Yes. Okay. So now we can look at the frequency response of the entire assembly of the op amp. So stage 1, stage 2, stage 3, all combined. What is the frequency response of this whole assembly? So how do we do that? We want V out over V in, correct? But in part 1 of the question, we obtained the frequency response of stage 1, right? What is the frequency response of stage 1? It is given by V out over V in of stage 1 alone. So that is V1 over V in. Yes? And what about stage 2? So stage 2 alone is V out over V in, which is V2 divided by V1. Yes? Then what about the frequency response of stage 3? So stage 3 alone will be V out divided by V2. So the frequency response of stage 3 alone is V out divided by V2. But we want the entire thing. So this entire assembly, what is the frequency response? How to find it? Okay. The trick is to know that for multiple op amps lined up together, the total gain, the total frequency response of the entire thing is given by the product of the gains of each stage. Okay. Product of the gains of each stage. Why is that? Okay. Let us take a look. Okay, I said the product of all the gains, right? That means I take the gain, the frequency response of stage 1, frequency response of stage 2, frequency response of stage 3, multiply them together. Okay, so that means V out over V2. Okay, this is stage 3 first, times V2 over V1. This is stage 2, and V1 over V in. This is stage 3. Okay, I will label this for your clarity. This is stage 3. This is stage 2, this is stage 1. Now, why is it the product? Notice this. You see, this and this are the same. So what would they do? They can cancel, right? This can cancel with this. Then look, this and this are the same. So what can they do? They also can cancel this and this. What are you left with? The only surviving terms left are this and this, which is V out over V in, which is what we wanted, right? You see, this and this are the same. That's why for multiple op amps, the whole frequency response of the entire assembly is given by the product of each stage. Okay, it's given by this derivation that I've done here. Okay, so that's why that is the case. Okay, but we don't go cancel this. This is just to show you why is this the case? Why do we multiply all the op amp gains together? So let me just rewrite it. Okay, so V out over V2 times V2 over V1 times V1 over V in. Okay, so we need to go back to the first three things that we did, the first three gains that we have derived, and then sub in these values, right? So you need to sub in this, and then sub in this one, and then sub in the first one also. So the first one is here, right? So let us collect these terms and then plug it into the equation. So what you get is, okay, we just do this, negative RF over R1 times negative R divided by R plus 1 over J omega C1 times negative 1 over 1 plus J omega C1 R. Yes, so I can do some simplification. So this negative and negative can cancel. And then I will just multiply this together. So like this, RFR divided by the denominators multiplied together. So R1 times this times the last one. Okay, no need to simplify this. You can just leave it as it is. Okay, done. Okay, so that is your V out over V in of the entire assembly. Moving on. What is the role of stage 1, stage 2, and stage 3? Okay, now we have to know what is the practical application of each of the op amps. Remember I said at first it might not be clear to you what op amp practically does, but now we had to identify it here. So now is the time. After you mastered your analysis, you know the basic three rules: V plus equal to V minus, I plus equal to I minus equal to 0, and then you do KCL. Now is the time we can finally grasp on what we have been doing all along. Okay, and this is especially true because we have been solving for the frequency response of all these op amp systems. Okay, these practical purposes are only unveiled, is only understood once you can find the gain of each of the op amp problems. Okay, so let us look into this. So stage 1, okay, when you want to identify the role of the op amp, you must look at the gain, okay, the V out over V in for each of these stages. So let us look at this gain of the gain of stage 1. So stage 1, we have V1 over V in. Now, the V1 over V in is negative 1 over 1 plus J omega C1 R. Okay, I just copied down from the top. Okay, the only thing we can do is to try to identify. Okay, as far as this course is concerned, as far as MA2009 is concerned, we have two uses of operational amplifiers. Number 1, filters. Number 2, amplifiers. Okay, so we need to identify which of these two, and then like if you know that is a filter, right? Whether it's a low pass filter or high pass filter. Offhand, you can tell it is a filter. Why is it a filter? And why can I automatically tell it's a filter? Because I see omega in it. When you see omega in it, it is automatically a filter. Now, why is this the case? Because remember I said filter, you need a criteria to filter out certain currents from the others, right? And what is that criteria we've been using? We have been using frequency. So once you see frequency exists in your gain, that means you know there's a dependence on the frequency. So that is the criteria provided for the filter to block out some frequencies and let through the others. Okay, so that's why whenever I see omega, I kind of tell I can kind of tell that it is a filter. Now, which type of filter? We have to do our limits, right? Low pass filter or high pass filter, we need to take the limit tending to 0 and tending to infinity. So let us just do that. So limit omega approach 0. Now, technically, I should do magnitude of h. Okay, so when you take the magnitude of this, the negative will go away, correct? So 1 over 1 plus j omega c1 r. Oh, sorry, I need to put the limit here. Okay, so when the limit of this goes to 0, sorry, when omega goes to 0, this whole term disappears, right? This whole term goes to 0. What are you left with? 1 divided by 1. 1 divided by 1 is just 1. Okay, now we look at the high frequency limit. So as omega go to infinity of 1 over 1 plus j omega c1 r, omega approach to infinity, this whole term approach to infinity, 1 divided by infinity is equals to 0, right? 1 divided by a really big number is equal to a small number. Now, what type of filter is this? Can you tell me in the chat? At low frequencies, there's 1. At high frequencies, there's 0. So it is, yes, low pass filter. Thank you. So this is low pass filter. Okay, so we have answered what is the role of stage 1 already. Okay, now let us move on to the role of stage 2. So stage 2, limit omega. Oh, sorry. You know what? Let me just recap again. Okay, it's important for you to solidify like just looking at the gain first. So when you look at the gain, which is V2 over V1, the gain is negative R plus 1 over j omega c1. Okay, I just copied on this gain from the one we derived. Now, see, this is the gain of the stage 2. We see that omega is present. That means we know it's a filter. Okay, so when we know it's a filter, ask yourself now, is it a low pass filter or a high pass filter? So we just need to take the limits again. So limit omega approaches 0 for this expression. Again, I should take the modulus of this. So modulus this means this will go away. Now, as omega approach 0, this approach 0. When you focus on 1 over 0, 1 over 0 become infinity. Okay, in the denominator, it is something plus infinity, which will also be infinity. Okay, so something divided by infinity will just all go to 0, right? Some number divided by a very big number is equal to 0. Now let us take the high frequency limit. Omega approach infinity. R divided by R plus 1 over j omega c1. So omega goes to infinity. This goes to infinity. 1 over infinity will go to 0, right? 1 divided by a very big number. This whole thing will go to 0. And then you see, R divided by R is only left, right? R plus 0 is just R, so this can go away. R divided by R is just 1. So I think it's not exciting for you anymore because you're already a master at this. So at low frequencies, there's nothing. At high frequencies, there's something. That means this is a high pass filter. Okay, so we have answered the role of stage 2. So stage 2 is a high pass filter. Okay, now we look at a new case which we've not encountered so far, and that is stage 3. So stage 3 shows this. This is the gain of stage 3. Sorry. So notice that there's no omega existing here, correct? So you know it cannot be a filter. Why it cannot be a filter? Because a filter needs a criteria to filter, right? And that criteria is angular frequency, which does not exist here. You don't see any omega, correct? Now, let me rearrange this equation first. So V2, I will move it to the right. Okay? So what will I get? V out is equal to negative RF over R1 times V2. Correct? Why do I move it like that? When you look at stage 3, right? Okay, let me go back to a picture of stage 3. When you look at stage 3, the individual gain of stage 3 is given by V out over V2. And V2 is the input, it's considered the input for stage 3. And V out is of course, is the output, right? Now, let us go back to this rearranged equation for the gain. I show it to you like this. What does that mean? It shows me that the output that I get from stage 3 is given by, okay, let me just draw a basic stage 3. Okay, don't care what stage 3 is. We just know, we just saw it from the top, right? I supply V2. Yes, I supply V2. I supply this with V2. And then out comes my V out. What does this equation tell me? This equation tells me that when I supply V2 into the input, what I get from it is this. Some number multiplied by V2. Let us not talk very abstractly. Let us just plug in some numbers. Let's say that this one is 20. Okay, let me just say that this is 10. And then this is 2. Okay, so 10 divided by 2 is 5. Okay, so this will evaluate to negative 5 V2. What does this show? This shows that if I supply V2 into my stage 3, I will get negative 5 times V2. You see, no matter what number I plug in, right, RF and R1 are just constants. They're just numbers, right? In this case, I plug in 10 and 2, and I'll get negative 5 here. What this means is that I supply an input, my output, I will get some number multiplied by the input. What is this? This effect is called an amplification. Amplification. What does that mean? It just means I scale my input, right? I get V2, and then out comes 5 times of V2. Okay, forget about the negative sign first. Just look at the positive version of all. Okay, so I input V2, I get out 5 times of V2. That is what you call amplification. You scale your input by some value. In this case, I scale it by 5. So if my amplitude is only a unit of 1 in my input, and then I pass it through stage 3, I amplify it, and then I'll get 5 times of V2. Okay, so this is what you call an amplifier. Now, this time we cannot ignore the negative sign. So what does the negative sign tell us? The negative sign tells us that it will invert the input. Now, what does invert mean? Okay, let us say that I have this V2 has a formula, is given by this. Okay, so let's say V2 is 1, is the amplitude of 1, sine omega t. Okay, so if I want to draw this very basic waveform, it will look like this, right? This is the V2. Then what about V out? If I want to plot V out, it will be 5 times of this, and then it will be the negative version of V2. Okay, it will be 5 times taller, so the amplitude will reach like 5 times. But not only that, it is not only 5 times taller, it is also inverted. What does inverted mean? It means all the negative numbers become positive numbers, and all the positive numbers become negative numbers. You see, in this region, V2 is positive, right? But then if I multiply negative 1 to it, then it will become negative, right? Negative times positive become negative. So yes, it will become 5 times taller, but it will also flip. So it will go down like this, and it's 5 times taller. And then you see, this part is actually negative, but if I multiply negative, negative times negative give me positive. So it will jump up like this, and it's also 5 times taller. So altogether, when you see that this is a negative, this tells you that it is inverting. Okay, the proper word here is called inverting. Then you see it's scaled by some number, so it is called an amplifier. Together, we call this a inverting amplifier. That is what inverting amplifier is about. Okay, amplify means I scale it by some number. Inverting means I change the sign. Non-inverting is when it is positive, right? If it's positive, then it retains your sign. Okay, it's just, it never changes your sign. It never flips the direction of your voltage, right? So that would be called non-inverting. Means I didn't flip the direction of your voltage. Okay, so this is an inverting amplifier. I see a message in the chat. Is there any message? Even if the value is, yeah, okay. So very good question. I wanted to say that also. So what happens if the scaling value is less than 1? Let's just say V out is equal to half of V2. Yeah, it's called amplification, but we call this an amplification with a scale factor of half, right? If you want to give it a fancy word, you reduce the input, right? So it's called attenuation, right? You reduce the input. Attenuate means getting weaker, okay? In English, attenuate means getting weaker. In circuits, attenuate means I make the amplitude of the input smaller, right? So it's a good question. What if it's less than 1? Yeah, it's still called amplification. Like, you know, when you learn about transformation in mathematics, you call it enlargement, right? But what if you have an enlargement with scale factor half? You still call it enlargement, but then with a scale factor of half. Okay. Likewise, even though the scale factor is reducing the input, we still call it amplification. Okay, so it's still called an amplifier. So that was a very good question. Okay, we will move on. Okay. Okay. So in part 5, what did they tell us? They tell us that now the input at the very start of stage 1, okay? This input is at the very start of stage 1. We supply an input that is described by this behemoth, okay? This whole monster of an equation. And then they give us the values of, you know, the resistors, the capacitors, blah, blah, blah. What they want us to find the output voltage. So remember in the part 3, we already got the frequency response of the entire system, okay? The frequency of the response of the entire system, which is V out over V in. Now we can use this, and then we got the gain, right? Just now the gain was also a monster. Yeah, it was the very big gain. Okay, I don't want to write it. It's the very big gain. Using this, we want to find V out, right? We want to find V out, so we have to multiply this over. But it's a bit difficult to do so. You realize that the gain itself, you know, from what we got, it was to recap, it was negative RFR, blah, 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 the very big denominator also, times this, which is also very big. Now, what is the step to take into doing this? You see, notice that they are made up of multiple waveforms of different frequencies, okay? Notice that there are different frequencies. This, and this. There are different frequencies. How do I know they're different frequencies? Look at this. In front of the T, in front of the T, in front of the T, there are different numbers. So there are different frequencies, okay? The number in front of the T shows the frequency. So that means you cannot change this to phasor, change this to phasor, change this to phasor, add them up, okay? You cannot. That is conceptually wrong. Why? Because when you add things together with phasor, they need to be the same angular frequency. Okay, same angular frequency or frequency. Okay, same frequency. Then you can add them up as phasor. In this case, you cannot do that. Okay, cannot change them to phasor and then add them up. So how? That is, this question tests your understanding of the practical use of the op amp. Now, because there are different frequencies, what does that mean? And above just now, we have identified that the some rows of each of the stages act as a filter. Don't forget that some of them were filters, correct? And then now we have different frequencies. So what will those filters do? They will block out some of these waveforms. So let me call this like waveform 1, waveform 2, and waveform 3. Okay? So 1, 2, and 3, they have different frequencies. And the filters will inevitably have to block out some of them because their frequencies are different, right? So that, what does that mean? We have to go back, go to the filters, the stages which are filters, and then find out their cutoff frequency. Okay? When we find out their cutoff frequency, then we can tell who of these will get filtered out. Okay? So let us go do that. So if you go back and then you recap, you'll notice that, hold on, let me just check my solution. Okay, so let us look at the low pass filter. Okay, just now we have seen that there's a low pass filter, right? Now we have to find its cutoff frequency. So remember, to find cutoff frequency, you need to solve this equation. So magnitude of H is equal to H naught over root 2. What is H naught? H naught is the max gain. And we found that the max gain is 1, right? The max gain is given by the non-zero limit. You take the limit to 0, you take the limit to 0. One of them will be 0. The other one is some non-zero value. In this case, is 1. So you take 1. And then this magnitude of H, I will just copy it down from the top. Okay, so okay, so magnitude means I don't need this. Now, the step to take is look at the top, make sure they're the same. In this case, they are. Both of them are 1, right? And then modulus of a whole fraction, okay, just recap your complex number, modulus of ZA, modulus of ZB, I can just split it. So like that, over like that. Can? So that means this modulus, I can split it, right? But then what is magnitude of 1? It's just 1, right? 1 is already positive. So I don't need the top modulus anymore, right? And then since the top are the same for a fraction, since the top are the same, the bottom are also the same. So I can equate the denominator, right? So equating the denominator, I will get modulus of this complex number equal to root 2. What is modulus of a complex number? It is given by the formula root of a squared plus b squared. A is the real part, so square root of this, and b is the imaginary part, so this, those that are beside the j. Okay, so square both sides, this square root and square root can cancel. This 1 squared becomes 1. 1 I move over becomes minus 1. So 2 minus 1 is 1. So it becomes like this. Okay, so square root both sides to get rid of the square. So this square can go away. Square root of 1 is just 1. And then I want to make omega the subject, right? Because we're looking for cutoff frequency. So move these two to the other side. You'll get 1 over RC1. And this is the cutoff frequency. Yeah, I should write here cutoff for the low pass filter. Now you sub in the value. Okay, you have to sub in the value so that you can identify the number. You sub in the value, which is this 10,000 times 0.8 nanofarads. You will get 125,000. But this by default is in radian per second. Okay, I will convert this to frequency. This is omega. I want to change it to f. Okay, remember that omega is equal to 2 pi f. So to get f, I get omega divided by 2 pi. So omega divided by 2 pi. So if I divide this by 2 pi, I will get about 19894 hertz. Okay, let us keep this in view. We need to look at this later. Okay, and keep note that this is the low pass filter cutoff frequency. Okay, moving on to the high pass filter. We also need to find the cutoff frequency. So cut off frequency. To find the cutoff frequency, we need to take the modulus of h naught divided by root 2. Hold on. Okay, so sorry. I will, yeah. So for the high pass filter, you copy down the gain is this r plus 1 over j omega c1 is equal to 1 over root 2. Okay, so modulus means the negative, I can drop it. Now look at the numerator. Are they the same? No, they're not, right? So I have to force them to be the same. Here is 1. Here is r. So how do I change r into 1? I need to divide it by r, right? So look at the fraction, divide all the terms by r. So this divided by r, this divided by r, this divided by r. Okay, so at the top, r divided by r becomes 1 over, at the bottom, r divided by r is just 1 plus this becomes 1 over j omega c1 r. Okay, and then this modulus, I don't need to do it to the top anymore because modulus of 1 is just 1. I will just take the modulus of the bottom. Okay, now that the top are the same, that means the bottom are the same. So equate the bottom. So the bottom means I need to find the modulus equals to root 2. Okay, I'll skip that step and then straight away jump to the modulus. So modulus is 1 squared plus 1 over, sorry, omega c1 r squared equals to root 2. So this and this go away. So 2 minus 1 is 1. Okay, and then square, I bring it to the other side, it becomes square root. And then if I make omega the subject, it will become 1 over r c1. Yes. Wait. Sorry, it's RC. Oh no, wait. Okay, let me see. Oh, sorry, it's 2. It's 2. Sorry. This is 2. 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 Okay, sorry. The unexpected visitor startled me, so I lost my concentration, admittedly so. Okay, so plug in the number, you get this, time 1.6 times 10 to the power negative 9 equal to 62500. Again, by default, this is radian per second, right? I want to change this to, what is it, radian per second? I want to change it to hertz. So divided by 2 pi. I will get 9947. So this is the 9947 hertz. This is the high pass frequency cutoff. The cutoff frequency with a high pass filter. Yes. Okay. So let us plot a body plot of each filter. Okay. So let us start with the high pass filter. Okay. Let's forget about gain right now. Let's just do like this, And then we know that the cutoff frequency is 9947 hertz. So label this as 9947 hertz. Okay, now let us go back to the low pass frequency. So low pass will be like this. There's something at the low frequency end, nothing at the high frequency end. Okay, so the what do you call this? Cutoff frequency is 19894. Okay. Wait a minute. Okay. The thing that I was supposed to do is make these two to scale. Okay, what do I mean? See, the number 19894, right, which is the cutoff frequency for the low pass filter, is way higher than this. So I should put it to the right of here. Okay, so sorry. I'll do like this, something like this. That. Okay. So let me extend this axis, sorry. This is 19894. Okay. Now, why do I make it to the same scale? And why did I even draw these two Bode plots? Actually, it's unnecessary for you to draw the Bode plot, but I want you to have an understanding of what is going on. Remember that what we did is we multiplied the gains of all the stages, right? Stage 1, stage 2, stage 3. I multiply the gain. Now, here, the y-axis gives the gain, right? The y-axis gives the gain. What I'm supposed to do is mentally multiply these two graphs together. Now, how to do that? Focus on each of the sections. So I focus on this section here. You see, the filter, effectively, what it should do is block out the frequencies until it becomes 0, right? So let us just treat this as 0. Okay, treat this one also as 0. Okay, it shows that it's filtered out. So when I look at to the left of this green line, okay, to the left of this green line, 0 times something should give me 0, right? So this is the gain of the whole system, the entire system. So entire system, the gain will be 0 times something, give me 0. Now let us look at the middle section, right? Here and here. See, both of them have something. Something times something will give me something also. Okay, let us just forget about what that something is. But we know that both of them are non-zero, right? Something times something will give me a number that is not 0. Now look at the last section. Here, 0 times, actually this will extend, right? This will extend like that. 0 times something should give me 0 again. So down here, it becomes 0. So here's 0, here's 0, here is something. And then we know that this is the low cutoff frequency, which is 9947. This is the high cutoff frequency, which is 19894. Yes? Now, let us go back and look at the input voltage that we have. See? Yeah, I'm going to copy this and then paste it down here. Take a look at the input voltage. The frequency in hertz of each of these waveform is 1000, 15000, and 80,000, right? Check if these will get filtered out or not. So where is 1000? Let us focus on 1000 first. 1000 is somewhere here, right? It's below 9947. It's below 9000. So it's definitely somewhere inside here. Do you see what is the value of the gain? 0. What does that mean? That means that this waveform will be blocked out by the filter. Okay? That one, because 1000 is here below the cutoff frequency of the high pass filter, it will become 0. So what that means is, at the end of the day, this goes away because it gets filtered out. It's filtered out. Now let's check 1500. Where is 1500? that is between the two cutoff frequencies, right? 1500 is somewhere here, correct? It's between 9,000 and 19,000. So look at the gain. It's something. What does that mean? That means this waveform, waveform 2, is allowed to pass through. It does not get filtered out. Okay. Next, let us check the last one. 80,000. Where is 80,000 on this graph? 80,000 is above 19,000, right? So it's above 19,000. That means the gain is 0. So what will happen to it? It also gets filtered out. That means this can go away. That is why we have been finding the cutoff frequency, so that we can see whether or not these waveforms will get filtered out or not. You check their frequency inside the waveforms. You see, this one 1000. So it will get filtered away because of because of looking at these cutoff frequency, this and this. See, 1000 is below 9000, so it gets filtered out. Then 15,000 is between these two, so it stays, okay? It stays, it's allowed to pass through. 80,000 is above the higher cutoff frequency, so it will go away because it gets filtered out also. Okay, so that is what we have been doing all along, just filtering out all these waveforms. Okay, so that means effectively our input voltage has been simplified. It's been simplified to only this anymore. So just now it was that previous long tree waveforms, right? Now it's just one of them only because the other two have been filtered out. So now it's much easier to do V out over V in, right? So remember, for the whole thing, just now it was the very big equation, right? So there was this. Okay, so remember our objective is to find the output voltage. So you take this and then you bring this to the other side, right? Let me see my solution. Okay, forget about my solution. So what are we supposed to do? See, this is a sinusoidal wave, right? This V in is a sinusoidal wave. So let us copy this down. So V in is equals to 2 sine 2 pi, 2 sine 2 pi times 15000 t, right? Okay. We need to change this to a phasor, okay? Only then we can punch it into our calculator. So this is cosine, sorry, this is sine, I need to change it to cosine. So 2 cosine, copy the inside. Then I need to subtract 90 degrees. So change it to phasor, 2 at an angle of, copy down the angle, negative 90. Now that I change it to phasor, now I can multiply it to my gain. So I go back, I can multiply it to my gain. Okay, so I'm not going to do that. It's because this is so big, right? But you can substitute all these values yourself. So they already give you all these values. You sub it in here. You sub it in, sub it in, sub it in, blah, 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 blah. And then you multiply by the phasor. You punch it into your calculator. Okay, so let me see if I have the answers. Okay, yeah. You sub it in, you punch it to your calculator. You will get a phasor of 2.66 at an angle of 86.5 degrees. Okay, so I put my calculator in degrees. Then I change it back to time domain. So time domain means I copy down the amplitude. I put a cosine. I copy down the insides, so the frequency. And then I copy the phase. Okay, so this is how you do this question. Okay, does everyone get this part? Do you all understand what am I doing when I multiply the gains here? This colorful drawing. Okay, can everyone understand? Let me see. Okay, everyone? Sammy okay? Ain't okay? Unsie okay? Okay. Sherman says okay. Yeah, so I hope everyone understands what am I doing in this whole process of combining, multiplying their gains. Because I also want to find the cutoff frequency so that I can tell among these waveforms who will go away, who will vanish simply due to the filtering effect of the op-amp stages. Okay, so now I will move on. So moving on, this is question 11.2. Wait, let me check if I finished everything. Okay, I finished everything. So, okay, question 11.2 shows you this. This shows you some variation of current against time. Okay, take note, this is millisecond, this is microsecond. So you must account for that later. Draw the voltage versus time when the load is a resistor. So what does that mean? It means if I put a resistor and then I vary the time, I vary the current like this through the resistor, what will the voltage look like over time? So this entire question, right, what is it testing? It is trying to test your understanding of the relationship between I versus R for a resistor, a capacitor, and inductor. Okay, so in a resistor, you should be already familiar what relates voltage to current. That is the classic Ohm's law. Right? It's the only thing that relates voltage to current. So V is equal to I times R. Okay, so what does that mean? That means the potential difference across the resistor is given by the current that goes through the resistor multiplied by the resistance. And this graph gives you current already, right? So what does current times the resistance mean? It just means I scale this graph by the resistance R, right? I just scale the graph by the resistance R. I take the current, I multiply it by R. So all these values that you see here, all these values, I multiply it by R. So what you expect is it will be a taller graph, right? It will be a taller graph, right? So that's what it means. So for a simple resistor, the voltage is just a scaled version of the current. So let me see the chat. Okay, nothing. Okay. So here's the current versus time graph, and this is acting through a resistor. So what we need to do is we look at the points of interest and we multiply them by R. So some points of interest are, for example, the segments, right? You can see that there are clearly 3 segments, like 1 here, 2 here, 3 here. So at the endpoints of the segments, we just multiply them by R so that we can get the coordinate and then plot them. So here and here, right? Here the number 1 here, the current is 5 milliamperes. So let me prepare my solution. Yeah, so 5 milliamperes, I need to multiply this by the resistance. The resistance they told me is, see, 10,000. So 10 kilo ohms. So sorry, this is V equals IR. This is I and this is R. So V is 5 times 10 to the power of negative 3. And then this is 10 times 10 to the power of 3. So this will give me 50 volts. So I know that the value of the potential difference here must be 50 volts. And then look at here, it's also 50 volts because the current is still 5, right? So 5 times, again, the resistance 10,000 will be 50 here. And then it will drop down to 0 here, right? Here the current 0, here the current 0. 0 times R is just 0. Here also 0 times R is just 0. So let me plot out the graph. So for the resistor, it will look like this. Right? It's just the same time, 0, 3 microseconds, 6 microseconds, 7 microseconds. So it starts from the origin, it goes up to 50. So this is 50 volts. Then constant, then goes down back to 0. Okay, so for a resistor, it's quite simple. It's just a scale version of the current time graph. What about for an inductor, right? What is the relationship between voltage and current in an inductor? You have to remember this formula. It is given by V equals to L di dt. Okay? Okay. So we are given the current time graph, right? It's the same current time graph here. What is di dt on the current time graph? Can anyone tell me in the chat, please? Di dt is anyone? Anyone? What part of it is it on the graph? Slope. Very good, Sherman. Okay, so di dt on this current time graph is the slope. That means to get the voltage, right? We are interested in the voltage time graph. To get the value of the voltage, I need to take the slope of the graph multiplied by the inductance. Okay, so that means we need to separate out these segments. So here, here, and here. Okay, this horizontal line, automatically I know the slope is 0, right? A flat line has no inclination, so the gradient is 0. So 0 times the inductance will still be 0. So that means the voltage value here is 0. Okay, what about this? We need to find the gradients. We need to find the di dt. So this is a straight line. We can just simply use the y2 minus y1 over x2 minus x1, right? Rise over run. So for t running from 0 to 3 microseconds, okay, let us look at the coordinates of the point. So for a straight line, you need 2 points. One is the origin, so 0, 0. Another is up here. So here, the coordinate is 3 microseconds, 5 milliamperes. Okay, so y2 minus y1, x2 minus x1. So this is y2, this is y1, this is x2, this is x1. I just sub it in, right? So 5 times 10 to the power of negative 3 minus 0 divided by 3 times 10 to the power of negative 6 minus 0. This will give me 5,000 divided by 3, which is about 1666.7. Okay, volts. Then, what about the last segment? The last segment here, the coordinate is 6 microsecond, 5 milliampere. And then down here, it goes to 7 microseconds, 0 milliampere. Okay, so you find the di dt, which is the gradient. So from 6 to 7, from 6 to 7 microsecond, L di dt. Oh, sorry, I forgot to do the L di dt, right? So we want to find the voltage value between 1 to 3, right? 1 to 3, notice that the gradient is constant. The gradient here is constant, and then V is given by L di dt. L is a constant, it's just a number. Di dt for this segment is just a constant, right? Because the gradient never changes. It's a straight line. The gradient never changes. So throughout this value, you have a constant multiplied by a constant. So from 0 to 3 seconds, on the VT graph, it is just a straight horizontal line, okay? Because the gradient is constant, multiplied by the inductance, which is a constant. So it's just a constant straight horizontal line, okay, on the VT graph. So let us find the value of V. Remember, the value of V is given by L di dt. And we've already found di dt. Di dt is given by this, right? Sorry, this one. So the L is 15 millihenries multiplied by 5,000 divided by 3. Punch this in your calculator, you get 25 volts. So from 3, sorry, what's this? 0 to 3 seconds, 0 to 3 seconds, it is 25 volts. Then remember, in the horizontal line here, di dt is 0. So from 3 to 6 seconds, V will be 0. So V from 3 to 6 microseconds. Okay, let me just write this down. So L di dt is equal to L times 0 because it's a flat a flat line, so no gradient. So this will be 0. Then the last segment, 6 to 7 seconds. So L di dt is given by 15 millihenries times the gradient. So the gradient is given by this y2 minus y1, x2 minus x1. Okay, don't forget to account for the micro and milli. This is milli, this is micro. Then you punch this, you should get negative 75 volts. So what is the shape of the graph? I'm going to recap again. This is a straight line. Straight line means the gradient is constant, right? And then to get the voltage, you take L times the gradient. L times the gradient. So if a constant multiplied by a constant, then on the voltage line, on the voltage graph, V against the T, it will be a flat line, which is constant, okay? Flat, constant line. And in this case, the value is 25 volts. Then here we have the flat horizontal line. No gradient means it is 0. So you drop down, and then this is 0 from 3 to 6. Right? And what about the last part? 6 to 7. We've identified that the voltage is negative 50, negative 75. Again, this is a straight line, constant gradient. So that means voltage is constant also. Constant but flat horizontal, okay? At negative 57. So drop down, go to negative 75, and then go back up to 0, like that. So this is your voltage time graph for the inductor. So it's just two rectangles, this rectangle and this rectangle, and a 0 line over here. Okay? Now, moving on to capacitor. So what will relate voltage to current in a capacitor? The defining equation is I is equal to C dV dt. Notice that this is a differential equation, right? Because we need to find voltage. We need to find voltage, but now voltage is inside here. It's inside this ddt operator. It's inside here. So we need to take it out, so to speak. So how do you do that? So the trick is first move C to the other side. So I become this, right? What I'm essentially doing is take C, move it to the denominator. So I just say 1 over C times I dV dt. Now we need to solve this differential equation. So move dt to the other side. So IC dt to dV. Now we need to integrate both sides. So integrate this, integrate this. Notice that 1 over C is a constant, right? So I can just pull it out the integration. So this is 1 over C, integrate I dt. We need to define the bound of the integrals, okay? The bound of the integrals. So we start from 0 seconds, time equals to 0, to any time we want. Let's just call it t. Then here, we start from a voltage value of 0, and then we go up to some voltage value that we want. So when you do this integration, you get V. You do this integration, what will you get? You get okay, what does this mean? You actually cannot do this because you don't know what is I. Now you have to interpret what this means. Okay, so let me just rewrite this. So I'll move this one here. So I equals this. Move this to the other side. Now you have to interpret what this integral means. Okay, what does this mean? This actually means the area of the IT graph, right? Integral actually means area under the graph. Area of IT graph. But, you see, notice that the bounds of the integral is from 0 to t, 0 to t. What does that mean? It is not just the area of the IT graph, it is the area of the IT graph accumulating from time equals to 0. Okay, what does that mean? I'll show you what I mean later. Okay, so so to find the value of the voltage in the capacitor, we need to find the area under this graph over here. All right. So let us find the area for these segments. So I'll cut up the segments like this, like this. We need to find this area first, right? So if I want the voltage up until here, which is until 3 seconds, so V of 3, that means I take 1 over C multiplied by the area from t equals to 0 to t equals to 3, right? This is what I mean. The area of the IT graph accumulating from time equals to 0. Okay, that is what I mean by this integral here. So 1 over C times the area from t equals to 0 to t equals to 3, which is a triangle, right? So you take, you sub in the number, and then area of triangle is given by half base height. So half times the base times the height. Okay, when you calculate this, you should get 25. Okay, so by the time you reach 3 microsecond, the capacitor will have 25 volts of potential difference. Okay, now let us move on until the second segment here at time equals to 6. So V of 6. So let us just use this again. So 1 over C, the integral from 0 to 6 I dt. What does this mean? This means I take 1 over C multiplied by area from time equal to 0 to time equals to 6. Okay, so what does that mean? Area from time equals 0 to time equals 6 means from time equals 0, I need to find the area until time equals to 6. So basically, this trapezium here, okay, this whole trapezium here, I need to find this area. Okay, so plug in the numbers, you will get 1 over 0.3 times 10 to the power -9. So for a trapezium, the formula for area is half height A plus B, right? This is height, this is A and B. A and B are the parallel sides. So half times height times A plus B microseconds, you get 75 volts. So by the time it reach time equal to 6 microsecond, it will accumulate 75 volts of potential difference in the capacitor. Okay. Now what about the last segment? So V7. So that means I take 1 over C times area from t equals to 0 to t equals to 7. Okay. So you plug in the numbers. Okay. So what does that look like? The area will look like this. So erase this. From 0 to 7 means I start from 0. I find the area, find the area, find the area, find the area until t equals to 7. So it's essentially the area of this entire thing, which is a trapezium. Again, half height A plus B, right? This is the height. This is A, this is B. So we plug in the numbers. Let me see if there's anything in the chat. I see a notification. Okay, nothing. So you get 1 over. Okay, so half height A plus B, you should get, which is about 83.3 volts. So by the time you reach 7 seconds, 7 microseconds, you will accumulate 83.3 volts of potential difference. Now, how to plot the graph, right? These are the values of each time segment. But what is the shape of the graph? That is also an important question. Okay, so let me just copy this. We've already found that at each segment, so at each segment, which is this and this, okay, this one, this one, this one, this one, we already found the value, right? So at time equals to 3, the value is 25 volts. At time equals to 6, the value is 75 volts. Time equals to 7, the value is 83.3. We know the endpoint values already, but what is the shape between the segments there, inside the segment? Okay, so let me just copy this. Okay, to find the shape, we need to look at the nature of the IT graph. And then remember this, V, we've already derived that V is equals to 1 over C integral of 0 to T of I dt. Yes, this means the area of the graph, right? Okay, that's, you don't need to know there's the area of the graph. The point is, to find the shape of the VT graph, you need to look at the IT graph. And then what do you need to do to it? You need to integrate it, right? So to get the shape of the IT graph, sorry, the VT graph, I need to look at the shape of the IT graph and find the integral version of it, right? Because we are interested in voltage. So we need to integrate the current to get the voltage time graph. So let us look at each segment. So let me call this segment A, segment B, and segment C. In segment A, what is the shape of the graph? It is just a straight line. Yes, straight line, remember, it is described using y equals to mx plus c. Right? We all know this from secondary school already. Straight line is y equals to mx plus c. I want to find the shape of this graph, right? So that means if I want to find the shape of the voltage, I need to integrate. Okay, forget about this constant. It doesn't do anything but scale it. So never mind about that. So if I forget about that scaling constant, it doesn't matter because it doesn't change the shape. It only changes the size. So integral of mx plus c, right? To get the voltage, I need to integrate the current. In this case, the current is described by a straight line. So I integrate this straight line. What will I get? If I integrate this with respect to x, I'll get right? I will get this. Now, what do I know from this? This is x squared. So this tells me that this is a quadratic function, quadratic shape, right? So if my current time graph shows a straight line, I integrate it to get the voltage, I will get this quadratic shape. That means this straight line will correspond to a quadratic curve, a parabola, from 0 to 3 microseconds, corresponding to this current time graph. Does everybody understand this? Okay. It comes from the fact of here. Voltage is given by the integral of my current, right? So I look at my current. My current is a straight line. I integrate a straight line, I'll get a quadratic curve. So that means between 0 to 3 microseconds in my what do you call this, voltage time graph, I expect to draw a quadratic curve. Now, remember that there are two ways of drawing a quadratic curve. It could be like this, or it could be like this, right? A happy face or a sad face. Which one is it? This is how we decide. We need to decide by looking at the coefficient here, right? Remember in secondary school, to decide whether it's happy face or sad face, you look at the coefficient. If it's positive, then it's a happy face. If it's negative, then it's a sad face. Here, the whether it's positive or negative is determined by the value of m. So let us go look at the value of m here. M gives you the gradient, right? M is actually the gradient of this straight line. See, the gradient of this straight line, is it positive or negative? Can anyone tell me in the chat? This y equals to mx plus c. Is the gradient positive or negative? Positive, yes, right? So because it's upward, right? It's upward sloping. That means this is positive. So we know that this is positive. Hence, the shape is this one, a smiley face. So we start from 0, then we curve upwards. Remember, we curve upwards until what? Until 25. So 0, 25. Like that. So this is a quadratic curve. Now, let us move on to the next part. So this is 0 to 3 microseconds. So from 3 to 6 seconds, what do we have? To find this shape, what is this? We need to integrate it, right? To get voltage, we need to integrate the current time graph. So this is a constant, right? Constant, let's just say is k. I integrate with respect to x. What will I get? K x plus c. You see, this is just a straight line graph. Okay. Now, will the straight line graph be going up or going down? We determine this by the gradient, right? So the gradient is given by k. The k is this value here. So this value is actually positive 5, correct? So since it is a positive gradient, so it is this one. Okay? So we choose this shape. So between 3 to 6, we will get this shape. And then it accumulate to 75, which we calculated just now. Yes? Now, what about 6 to 7 seconds? In this case, 6 to 7 seconds, also a straight line, mx plus c. Integrate this to get the shape. So we already done it here, right? In this case, the gradient is negative, correct? You see, up here is positive, but then this time is downward sloping. Downward sloping means this m is actually a negative value, right? So that means, okay, if right now this m is instead negative, right? This is negative now. So that means the coefficient of the x squared term is negative. Hence, the quadratic shape will be this one now, okay? Not the smiley face, it will be the sad face now. So, we need to reach 83.3, right? Which is what we calculate just now. So it will, you might ask me, do we take the left side half or the right side half of the quadratic shape? You see, let us take the right side half. If you take the right side half, you will have to curl down, right? Then we will never reach 83.3. Okay, so it cannot be this side of the quadratic curve. It must be the left side, which is like this. Okay, so actually the complete quadratic will look like this, right? But I just take the left side half. Then this will reach 83.3. Okay, and then that is your solution. So this is 7 microseconds. Done. Okay, so that's it. We've done the resistor, capacitor, and inductor. Yes. Okay, so oh, determine the total amount of charge at time equals to 7 microseconds. So for this, you need the formula C equals to Q over V. We want to find charge, right? So charge is given by Q. Then we plug in the numbers. And then by the time you reach 7 microseconds, you will get 250 over 3, which is what we calculated just now, which is this in coulombs. Okay, so that is your final charge. And we are done. Yeah, okay. So yeah, we've done tutorial 11. I will not cover tutorial 12 because it is on diodes, which is unnecessary for you, but feel free to peruse it on your own interest. And that's it. We finished all the tutorials that we need to. Yay. And with that, we come to the end of PTP. Oh. So in my last words and in my final recording, I guess I want to express my gratitude and having the privilege to serve you all for week 5 to week 12. Yeah, it's been a hectic journey and it's been a sad journey. Carry on. This is a this is a this is a GG2 question 1 hour 30 minutes. Yeah, I mean, honestly, a bit of it is my fault. I mean, I don't know why suddenly someone try to go in while I'm doing my PTP. Sorry, Samuel. It's actually not that long. It's just that I'm going slow for you all to understand it, right? Because I explained it quite thoroughly, but of course you won't need to explain to anyone during the exam, right? Yeah. So yeah, this is the last PTP. In week 13, there will be no more PTPs for circuits, which is good luck to you all then. So please study hard, work for your finals, get an A in my honor, and please carry on my legacy. Luckily, you went through. Yeah. What do you mean? Luckily, I went through. I had to go through. I had to go through with this question. Oh yeah, fair point. Yeah, because uh, in class tutorial only 1 hour, so your tutor might half ask this. Yeah. So actually, you all can leave now. Thanks, man. Yeah, no problem. Good luck for your finals, everyone. It is your CA2 next week. Let's go. I'm already dead, man. Toasted. Keith. Yeah, thank you, Keith. Y'all can go already. So it's been a pleasure to serve all of you. I've really enjoyed my journey as a peer tutor. I've been dreaming of this since my first academic year to be part of this wonderful journey. Better than my tutor. I'm very honored. I'm very honored. Thank you. I think I'll send out Google Forms for feedback, so you can feel free to add it in. I think I only put 3 questions, so you can just feedback on what I can improve on, and what you liked about this whole PTP journey. For me, I don't know. Even though I didn't serve much people, I find it quite a sentimental journey. I don't know. I think even though the class size is small, I kind of enjoy this class size at all because I don't know. It's been engaging. When I ask questions, you all can answer. It's not that boring, so to speak, because I know lectures can be quite dull. Lectures are quite dull for me, but I don't know because you have like Sherman answering me, and then Samuel answering me, and then Haran answering me. It's a nice journey, even though it's a small family. It's a happy family. So you can take over the prof. No. I do not have a PhD, so I'm not entitled to take over the prof. I'm wondering if I should continue to MA2009 next semester or move on to a different subject. You all have any mods you want PTP for? Any upcoming mods? Heat transfer? No, I have not taken heat transfer myself. 3003. I also have not taken 3003. I don't even know what that is. Yeah, so I don't know whether I should just stick to circuits or do something else. DTDX. Oh, until that's something related to temperature. You should do heat transfer. I hope. Let us wait until I can even master heat transfer in the first place, okay? Then we can talk. We can have a cup of tea and have a chat over it. Yeah. All the best for your finals revision. Yeah, you too, man. All the best. Get an A+. I know you can do it, Sherman. You've been with me from time equal to 0, from day 1 of PTP until now. You've never missed a class at all. Surely you can do it, man. Sherman for the win. Yeah, Samuel also. Oh yeah, how could I forget Samuel? Oh my god, Samuel's the rock star also. Yes, A star. No man, I've already seen his name in a PhD certificate for for a circuit related thesis. Uh, I actually don't feel like going. I don't feel like going because I don't know. Once I end this call, it's PTP is over forever. Oh yeah, on that note, since I'm ending my post for a peer tutor. Reader, if you have any more questions, redirect your questions to Professor Colin or Professor Domenico. Personally, for me, Professor Colin has been great help to my journey through 2009. In fact, he's the strongest inspiration for me to join as a peer tutor, to volunteer as a peer tutor, uh, yeah, for circuits. So really, if it weren't for him, there would be no me sitting right here talking to you all right now. Yeah. So do seek him out for help. He's a very nice, generous man. Don't hesitate. So you all can leave now if you don't have any more questions. I'm just gonna sit here and wait until the last person leaves my class and then cry off camera. Yeah, man. See you around, Sherman. If you see me around at school, say hi to me. You too, Samuel. See you forever. See you all. Thank you for being part of this lovely journey I have. I'm gonna miss this. Thanks for uploading these PTP classes on YouTube. Been a great help for me, honestly. Yeah. Um, I'm glad it could help Tamin. Uh, please share it with all your friends if they struggle in circuits as well. Go ahead, share this with them. I forgot to tell you all, you can all start on your PYPs now. Actually, the moment you finish tutorial 9, right? The moment you finish op amps, you can already start on PYPs. Yeah, so go ahead, start getting the rhythm, pressing your calculator, to be familiar with the flow of it. Really, everything will be fine for circuits. Really, circuits is the God sent module to MAE. And yeah, I'm really glad I can help you, Tamin. It's I don't know. For me, I was also struggling in circuits. After recess week, the lecture was quite unhelpful. But then I went to a crash Professor Collins class, then I really understood my way. Yeah. Maybe you can continue PTP by doing the exam question next week. Oh, you see, I also have exams to prepare for too, Tamin. So as much as I want to, yeah, I really thought of it, At the start of the semester, I thought of doing PYPs also, but I have no time anymore. And then week 13, I had to cancel my PTP for y'all to revise and for me to revise as well. I have I have some finals to take care. And if you're taking CC, you know that there's CC7 to do your submission, your video, and then your third proposal for the disgust me. Yeah, so I'm really sorry, Tamin. But Tamin, you don't need me to go through the tutorials because the MAE club already provides the solutions. Yeah, some of them are wrong, but then not a big fraction of them are wrong. So you can use the MAE club answers. I have been using the MAE club answers for my revision when I was taking 2009. So don't worry. Even though there's no uh, verbal explanation from me, I think the written solutions are already sufficient for you, Tamin. Is that okay, Tamin? I'm really sorry to disappoint you. Yeah. Good luck, Tamin. All the best, man. You can do it. Work hard. A plus is yours. And if you're good enough, this seat of the PTP will be yours as well. Be my successor, bro. Don't doubt yourself. This is a very fulfilling journey, you know. It's one that I've been going through for 7 weeks with you all. It's, but it's fine, Tamin. One day you will understand the glory of giving. Okay, I'm gonna stop the recording. So this is a personal message to my YouTube recording because I'm uploading this later. Um, thank you for the students who have been through with me through thick and thin from day zero, from time equals to zero, day one of my PTP, which I started late because they had to start late. But as I go through this journey, I see a lot of people expressing their gratitude, thanking me for helping them, which I'm really happy for because I didn't join in PTP to just be another lame tutor. I want to see you all flourish or get something out of get something different from class. So I'm glad I'm able to be part of that something different in your learning experience. Thank you all for providing me this wonderful opportunity to make a difference in NTU. Signing out, your MA 2009 PTP.